Today, we're going to talk about condition variables and semaphores, and hopefully that should position you well for the upcoming project, which will be released shortly. So this is going to be project 3. Please, again, follow all the assignment rules. Please read the PDF file carefully. So don't join someone else's group. We had these issues for project 1, for project 2, because you join someone else's group, then another student contacts me and says, oh, somebody took my group and whatever, right? So please check Canvas what your group number is if you are not sure, and join your group. The same thing for like submissions. You have to test it on lab machines. If it doesn't compile there, you may potentially get 0, right? So again, let's enforce it strictly for project 3. So you have to do due diligence. Also, some students submit at 11:58 p.m. right? So and then while they log into Canvas, it's already late. Yeah, so please make sure you submit it like at least maybe half an hour before the deadline, right? Because your browser can crash and so on. Okay, so last time we talked about data races and race conditions, and we specifically described the mutual exclusion approach, how we can, implement mutexes. We talk about specific implementations, Peterson's algorithm and Baker algorithm. We also look at the hardware implementations. So we also have we also have described how we can use it in pthreads, how we can use logs, and looked at some liveness issues such as deadlocks and live logs. So next, we're going to talk about condition variables, thread safety, semaphores. If time allows today, I will talk about reader-writer log, but I also want to do some, to introduce a little bit project 3, right? So if we have some time, maybe I will move reader-writer logs to the next lecture and talk a little bit about the project 3. Okay, so just to give some introduction about thread safety, quite a few functions through historical reasons were thread unsafe. So for example, sometimes we keep state across calls in functions such as str talk, which will parse the string and separate it into different components. There is also a rand call, like random number generator. All these things are not actually thread safe because they keep state in a static data. And remember that because we have the same address space, that effectively means that we will have if we use the same global variable, that will be shared across all threads, and clearly it's going to create data race and so on, right? So we don't want to use the same shared variable. So there are newer versions of these functions which are thread safe. So for example, str talk _r and so on. So there is also sometimes some functions return a pointer to a static variable. Unless it's a read-only variable, that's a problem, right? So, so you want to make sure that when you implement functions like this, you don't have the same problem. So get host by name, get host by address, and so on. Sometimes, you just access shared data without proper synchronization. This is in general known as race condition, as we talked about, right? So, and this will cause, certain issues. So please, when you design your code, unless you have to use a shared variable, never use a shared variable. So that's, I guess, the rule that you have to follow. So don't use global variables unless you have to use global variables, and so on, right? So those are general rules for good practice of programming. So like in manuals, you can see that, for example, for some functions like pthread create, it says thread safety, and then it says, okay, MT safe. That means it's multi-thread safe. So make sure you check this before you use this function. So for example, if you look at let's say our talk, and that will say that it's thread unsafe in the manual. So let's go back to the example with the queue. I mean, I think we looked at the circular in buffer queue, but let's just, generalize it, just a general queue, whatever we have, right? It's just maybe a general FIFO queue, or doesn't have to be even FIFO queue, maybe just a stack, doesn't really matter. So we will get, so the way that we will protect this queue, we will have a lock. So we'll have lock mutex, then we will, take the element from the queue and then unlock the mutex. And then we'll hopefully process this message that we retrieved from the queue. So, but now the natural question is, what if the queue is empty? So last time we looked at the condition where the in buffer was empty and we had to kind of unlock and then get a lock again. And, that would look cocky, right? So, and because that didn't look, that was not really good. So what can we do here? Well, first of all, we can check if the queue is empty, right? So let's say that generally speaking, we will say, okay, queue is not empty, then we are gonna take the element. What are we gonna do in the else statement? Well, in the else statement, we have to effectively, last time we were kind of spinning, right? So we were trying to see, okay, can we kind of spin and wait until the queue is has some elements. So the message can potentially be added to the queue. So what we did last time, we said, okay, we can just unlock the mutex and lock the mutex in this while loop. Okay, that's fine. But what is the problem with this? Any ideas? Okay. Yes. So busy waiting will consume a lot of CPU, and naturally, what we can do, we can just, sleep while the queue is empty, right? So that's what we can do, right? But then the question is, how much do we need to sleep here? Do I need to wait like maybe several nanoseconds, microseconds, milliseconds, whatever, right? Maybe several seconds or hours, who knows? I can potentially sleep for a little bit and go back, but that's not good. Again, that's kind of like cocky approach, and we don't want to do that. So what can we do here? Well, it turns out that there is a special primitive that can do this work for us. So it's called condition variable. So effectively, the condition variable will have the unlock, sleep, and lock operation kind of combined together, right? So we will have this cond wait, and there is a condition variable, and then we pass the mutex. So remember, we need to pass the mutex because we want to unlock the mutex, sleep, and then lock the mutex again. So we can effectively have cond wait, condition variable, and then pass the mutex. So, okay, but how do we let the other side know that there is some element in the queue? So for that, another thread, so by the way, why do we have two parameters? Because we have the condition variable and the mutex, right? So we want to make sure that the mutex is unlocked and unlocked, and condition variable is just, just some primitive that we will use to make sure for synchronization, right? So how do we notify this side? So the other side has another thread. We will add the message, we will lock the mutex, push the message to the queue. Let's say this queue is unbounded. Let's for simplicity, like last time we looked at the in buffer, but let's say this queue is unbounded. You can push as many elements as you want. And then you do const signal. Const signal will wake up one thread that is waiting. So, and then finally you unlock the mutex. So the const signal will not actually block. So it will just go and see, okay, there is some thread waiting. Let me wake up this thread. So it will mark this thread. It will unblock this thread. It will put it from the block queue to the ready queue. And now this thread will be ready to be scheduled next time. So now process one message will effectively unblock in cond wait. So again, cond wait just contains unlock, sleep, and lock logically, right? So you can just imagine the three operations there. And that's what quantum weight is, right? But the sleep is something that is, you don't have to worry about in deciding, okay, how long do I need to sleep? Because you have the other side, which will wake you up through the phone signal. So that is the what we call conditional variable. So now there are two versions of two ways we can wake up another site. There's one way we can do signal, it wakes up one waiting thread, just one waiting thread, like in this example. And there is broadcast, when we want to wake up all waiting threads. So sometimes we want to broadcast every single thread that is blocked right now. We wanna check, okay, is there anything that maybe there is some, maybe there is some condition you want to put, maybe you want to check something more than just put something to the queue. Maybe you want to check the queue if it has a certain element, and if it doesn't have that element, you want to go back to sleep and so on. So sometimes you want to wake up all waiting threads. But in this particular example, we didn't care which thread we wake up, just as long as we wake up one thread. So for one message, we will do signal. Maybe sometimes we want to do something more complicated, maybe like want a free memory chunk, then we want to do broadcast. So how do we do that with speed threads? With speed threads, we have this conditional initialization, conditional variable, and then we specify attributes. Remember, if you don't use any special attributes, you can just specify null there. Then cond weight, that's what we looked at, the conditional variable weight. It has conditional variable, pointer, and mutex, and the cond signal. So to properly use conditional variables, you have to define a conditional variable itself, as well as the mutex that you use with this conditional variable. Because remember that conditional variable weight has the second parameter, the mutex, that you will unlock and then lock again. So any questions about conditional variables this far? Is it clear? Okay. So when conditional variables are not adequate? Well, sometimes these notifications, like sometimes the thread that is supposed to be waiting, maybe it's not waiting right now, maybe it's descheduled or whatever, right? Maybe it has not started yet, and so on. So these notifications can be lost. So that means another thread adds something to the queue, issues pthread cond signal, but the other thread doesn't know that it was supposed to wake up because it hasn't started yet. So it didn't even reach it didn't really reach the point where it has to call conditional wait. So when it executes conditional wait, this cond signal will be lost because cond signal arrived before cond wait. So that sometimes is not acceptable, and we want to we want to preserve that information. We want to say, okay, there was some notification, even though it arrived before that cond wait, we want to kind of take that into account. So, and for that purpose, if you want to design something like this, for that purpose, we can use semaphores. So semaphores effectively provide this kind of memory when you can preserve all these notifications. So effectively, a semaphore is a combination of mutex and a conditional variable. So first, you can use semaphores for mutual exclusion, pretty much the same way as you use mutex. So semaphore is just more general. So in fact, if you just initialize semaphore properly, you can just replace all mutex occurrences with semaphores. So it can be used for waiting for conditions. That's like condition variables. Again, it doesn't mean that semaphores is exactly the same or can always replace condition. It's not. I guess but you can design the algorithm in a different way so that you will have that. So just keep in mind that it still has a different semantics. With condition variables, you don't care whether this signal arrived or not. If it's semaphores, you have to preserve that. So there are two operations. One operation is some weight, and in the original literature, so semaphores were invented by Dijkstra, so he used this P notation. So, and unless you know Dutch, it probably doesn't really make too much sense. So let's use some weight for simplicity. So, and then there is SemPost that is also in the original literature is known as V operation. So SemWeight effectively will decrement the semaphore. So the semaphore is effectively special, has an associated integer counter, and you will decrement the semaphore. And it will wait if semaphore is negative. So let's say the semaphore value was 0. It decremented the semaphore value, so now it's -1. So, and therefore it will wait. So now SemPost, so it will increment semaphore and wake up one waiter. So if there are waiters. So if there are no waiters, there is no one we can wake up, but it will do two operations, increment and wake up one waiter. So the definition, the full definition is it's like an integer with 3 differences. So when you create a semaphore, you initialize it to some value. Just whatever your algorithm requires. So we will talk about those, initial starting points. So then you will only use 2 operations, SemWeight or SemPost, to decrement or increment semaphores. You will not actually read the value of the semaphore when you started using it. I mean, of course, with speed threads, you can do some hacky code. You can probably read the semaphore value for debugging purposes, but that's not something that you want to do in general. I mean, that's not something that you should use in a good code, right? So, I mean, I'm not saying it's impossible, but, technically speaking, you shouldn't be doing that. And certainly any good algorithm, any, correct algorithm will not depend on that behavior. So when a thread decrements the semaphore, if the result is negative, the thread will block. So let's say the semaphore value was 0. So now it becomes -1. So the thread will block. So the semaphore value, let's say, was -1. It becomes -2. Another thread will block, and so on. So when a thread increments a semaphore, if there are other threads waiting, one of the waiting threads will get unblocked. So, by the way, in the syllabus, I mentioned this textbook. It's called the Little Books of Semaphores. So you can access it online. So it's free. It's not the main textbook, of course, for this course, but there are some useful examples you can check there. For example, how you can solve certain problems. There are some interesting problems, and how you can actually use semaphores to do that. I think it's very useful to understand how semaphores work. So we can also make an analogy with pens. So let's imagine that we have 5 pens right now. So 5 pens. So, and then let's say we need to write something, and for that we need to get a pen. So we initially have 5 pens. The semaphore value is 5. So I'm calling SemWeight. The semaphore value will decrement. So we'll take 1 pen. So 1 thread will enter, the critical section. So then we will do another SemWeight. So the semaphore value right now is 4. So the value will become 3. So another pen is taken. So another thread enters. So then again SemWeight. So semaphore value becomes 2. Okay. So then someone will call SemPost, maybe another thread that, maybe the producer that pushed something to the queue is calling SemPost. So the semaphore value will become 3. But right now there was no thread waiting, so no one was blocked, so there is no need to wake up anyone because we had sufficient number of pens. So now the semaphore value is 3. Okay, there is another sum weight. So the semaphore value will become 2. Another sum weight, semaphore value will become 1. So finally, the last pen is gone. Semaphore value is 0. So another sum weight comes. The value is now negative. So this is when we're going to block. So the semaphore value is now negative. Was 0. So once this thread called sum weight, it became -1. This thread has to block. So then another thread comes called sum weight. It will also be waiting. So in the semaphore value is -2 now. So finally, maybe the producer thread calls sum post. So now the value is again -1, and one thread wakes up. So the one thread will wake up. So that you can use as an analogy for like with pens, right? So one thing. Okay, so one thing I mentioned. So for binary semaphores, we can use mutex. We can replace mutex with a semaphore. So effectively, the initial value of the semaphore will be 1. So we'll initialize semaphore with 1. So when we call lock, that's going to be sum weight. So instead of unlock, we'll use sum post. So now the semaphore value is 1. So we effectively have just one pen. So once the first thread comes and takes this pen and enters the critical section, effectively this pen is gone, and now this thread is in the critical section. Another thread comes, the value is already 0. So that means it will be -1, it will block. Another thread comes, it will be -2, and it will block. So now the moment the first thread finish, it will call sum post. So the value will increment by 1, and one waiting thread will wake up. So that means that's pretty much what we had for mutex, right? So only one thread enters the critical section, one thread finishes, another thread wakes up. Okay, go ahead.
Does this method of implementing mutex take care of the busy waiting problem?
Yes, so we are not going to be busy waiting, right? So just like with normal pthread mutex, the thread will get descheduled, and will only be scheduled when lock is released, right? And similar, when the semaphore value allows to schedule one thread, it will wake up that thread. So it's pretty much the same thing. Okay, go ahead.
We call unlock more than one time.
Yes.
Does it still behave like the mutex?
Yes. So if you call lock multiple times, first time we call, it was the initial value is 1, so it will become 0. The first time you call it. Let's actually maybe draw it on the board. Okay. So yeah, so the first time you call lock, you're gonna get so the semaphore value was 1, right? So that will become semaphore value 0. But this thread can enter, right? So because semaphore value was non-zero initially. So now this second time you call log, let's say this is this thread 1, thread 2 calls log, semaphore value becomes -1. So this now negative. It has to so T2 is not allowed to enter, right? So now it has to wait because it's already negative. So another log, semaphore value is -2. T3 has to wait and so on. So now T1 calls unlock. That effectively will increment the semaphore value by 1. So the semaphore value is -1, and it will wake up one waiting thread. So that will wake up T2, because that was hopefully, if it's a fair scheduler, T2 has to be in the T2 has to be scheduled first. So maybe it's kind of 5 of you there, hopefully. And then the semaphore, so that will wake up T2. So T2 will now enter. And then when T2 is done, the semaphore value will be 0. And it will wake up another waiting thread. So it will wake up this thread. So T3 will enter. So finally, when T3 is done, the semaphore value again will be 1. And another thread that wants to enter will be able to proceed right away. So now let's say if there is T4 calls lock, it will be able to enter right away. Okay, go ahead.
I actually need if we still call unlock here after the T3.
After T3?
Yeah, after the T3 is unblocked, and then we call unlock again. That would
Well, that semaphore value become 2.
Yeah.
That is not like, and you cannot do that from Mutex. You cannot do unlock without
Yes.
locking first.
So that's what I'm saying. It's not. It doesn't behave like mutex anymore.
Well, but Mutex, you're also not allowed to unlock unless you locked previously.
Yeah. So in
So here we have to lock first and then unlock. Then we have to lock and unlock, lock, unlock. But we cannot just call unlock without locking.
yeah, we shouldn't do that, but we could.
Well, if you do that, I'm pretty sure it will. Though I think that Mutex unlock will fail also.
Yeah, because we're not limiting the capacity.
But you bring up a good point. Sometimes here the difference with Mutex, you cannot call unlock and then lock, right? So that would be not allowed. But in semaphores, sometimes you want to design a code. Maybe I shouldn't kind of make an analogy with unlock and lock, but sometimes something is effectively arriving first, and then the other side arrives next, right? So you cannot, so you can potentially reorder these operations, right? So with semaphores, it's totally fine to call sempost before semwait. With Mutex, it's not fine to call unlock before lock. So that's at least, I mean, it depends on the implementation, but the result is undefined, right? So because it can be anything. It can crash, it can do something wrong or whatever, right? So that means you cannot call unlock before lock. The semaphore is totally fine to call post before wait, if you are still sure that you are doing the right thing. So maybe there is some implementations, like some problems that we will look at that requires to call some post before some wait. And that obviously is something that we need to take into account, right? So with Mutex, we cannot do that. But semaphore is more general, I would say. Semaphore is more general. Okay, go ahead.
So calling unlock for an unlock with mutex is undefined behavior.
Unlock without lock, yes.
I mean calling and already unlock the mutex with lock with unlock.
I'm sorry, I didn't get it.
I'm saying if we try to call unlock on an already unlocked mutex.
Already unlock, yes, that's also undefined behavior, right? So we shouldn't be doing that. It's like you call free multiple times for allocated blocks. So you implemented malloc and you know that it will it's not going to work properly because you will treat it as like free block and then try to delete it from the free list and so on, right? The same thing can happen here. A lot of things may go wrong just because you call unlock second time. Sometimes pthread will have this capability to make sure that you don't call unlock multiple times, just like malloc has free, like we'll make sure that you don't call free for already free block. But you shouldn't be doing that, right, in the correct code. But again, it's totally fine to call sempost multiple times if that's what your synchronization problem requires. So and again, we will look at this. So semaphore therefore is more general. It doesn't have these restrictions that Mutexes have. So yeah, so in this case, we can just treat it like as kind of value 1 indicates unlock, and then 0 or less means it's locked. So semaphores can also be used as a signal. Obviously, that's our goal, right? To have semaphores, to use semaphores for something more complicated than just just a regular like mutual exclusion problem. So what we can do, let's go back to our original example with Q, which we for which we used conditional variables. So now for process one message, we will include some weight. So some weight is the first operation. So it's like taking a pen, right? So you have maybe a certain amount of pens. Initially, nothing is produced, the queue is empty. So that means you have 0 pens. So initially it will block. Then you get a lock. Eventually, let's say some of the producer, let's put that aside for a moment. The producer puts some element in the queue and you get 1 pen, maybe another pen and so on, right? So you have this lock mutex. Then you take something from the queue. Okay, you take this message from the queue and then you unlock mutex. You still need mutex because only one thread is allowed to modify the queue at a time. So make sure you understand there is some weight. Some weight allows basically synchronizes how many threads are ready to enter the critical section to grab this some element from the queue. Because there is, let's say there is 5 elements in the queue. 5 threads can now enter and grab the elements from the queue. So the semaphore value is 5. So any like 5 threads can take some element from the queue. But now when you actually take something from the queue, you still need to protect the queue. So only one thread at a time modifies the queue. So for that one, you still need a mutex. So finally, when you take this message from the queue, you process it, you unlock the mutex and then process the message. So there is no need to hold the lock once you've taken it from the queue. So by the way, you want to keep all critical sections as small as possible. You don't want to, you don't want to hold lock unless you really have to. So, if you need to check some error status, you can do that after you unlock it. As an example, maybe you want to add it to some local buffer. You can also do it after you unlock it. So now let's look at the add message. So that's the same deal. We have to lock mutex to access the queue. Only one thread at a time is allowed to access the queue. Whether it's adding or removing, doesn't matter. So we still have to protect the queue with the mutex, but now at the end, we have sempost. So one element was added to the queue. The semaphore value from 0 now was initially 0 and became 1. So now one consumer is ready to enter. Let's say another element was produced. The semaphore value is further incremented. It's further incremented, so right. Let's say we have maybe 3 producers. The semaphore value is initially 1. Then let's say we didn't call some weight at all, right? So the initial value is 0. And maybe 3 producers called add message. So we will have semaphore value 1, then 2, and then 3. So the semaphore value is 3. So now 3 consumers can call some weight without blocking. So they will immediately proceed without blocking because they effectively have this 3 pens already, which they can grab. Now the 4th consumer will of course block. The 4th consumer will block on the same weight. But now those 3 consumers that were able to enter to go past the same weight, they will still have to take element 1 at a time. So when you access the queue, you still have to protect it with the mutex because only one thread is allowed to modify this queue. So it doesn't make sense. So now the semaphore value will effectively also indirectly tell us how many elements we have in the queue. So if you have 5 elements in the queue, which are ready to be consumed, the semaphore value will be 5. If there's 0 elements, it's going to be 0. So if you actually already kind of more consumers, then it can be -1, -2, and so on, right? So the semaphore value will reflect how many elements we can already consume without blocking. Okay.
Would you be able to use 2 semaphores here instead of a semaphore and a lock?
Yes, sure. You can replace log with the second semaphore. That's a good question, right? So you can initialize the second semaphore to 1. So the first one may be initialized to 0 because that's assuming that you have no 0 elements in the queue. The second semaphore you have to initialize to 1, and then you will replace log with semWait for the second semaphore and unlock with post for the second semaphore. But again, because pthread provides both semaphores and mutexes, so we don't necessarily want to do that because hopefully mutex is potentially more optimized, for this case. So if you just need mutual exclusion, that means only one thread has to proceed to the critical section, then mutex is good enough. So you don't want to use semaphores, which allows more flexibility. So how can we use any other questions about semaphores so far? So just when you are in doubt, like remember this paradigm we had like with pens, right? So if you have one pen available, you can already take it, grab it, and enter the critical section. If you don't have any pen, you have to wait until someone calls sempost. So, and if the initial value is 0, that every first thread the very first thread that will enter will block because you don't have any pens available right now. So only when the producer puts something there, you can enter. So how can we use semaphores to track resources? So what we can do, let's say we want to limit how many threads we create based on the number of cores that we have. So we will initialize maybe the semaphore value to the number of cores, and then before we create a thread, we will put some weight. So that means, like, if I have 16 cores on my machine, I initialize the semaphore value to 16, and that means first some weight calls will not block. So I will be able to do thread create right away. So now on the 17th call, I will have to block and wait until someone calls sempost. So then let's say the thread runs, and when it's done, it will do sempost. So then maybe the 17th thread that I was about to create can proceed. So that way you can control how many threads you create so that you don't create too many threads that will flood your system, right? So maybe you can limit that, right? That's just one example. Again, it may be not that useful in practice, but helps to understand semaphores. So let me, I wanted to also talk about reader-writer logs, but let me instead do that next lecture. Today I will start, I will introduce what we'll have in project 3. And we will continue with reader-writer log in our next lecture. Let me, just give me 1 second. So for the third project, which is about to be released, and hopefully I will, release it sometime today. Maybe once the, late day for project 2 passes, maybe midnight, I will release it at that point. So we pretty much gonna work maybe till on project 3 till pretty much till the end of the semester, maybe except the last week, right? So maybe it will be due probably a week prior to the last week. And you have, I mean, it's up to you if you want to use your Thanksgiving break, but of course, when I assign the project, I'm not taking that into account. But if you feel like you need more time to complete the project, then You can definitely use Thanksgiving break, though we won't have any office hours during that period. So if you have any questions, better to ask before the Thanksgiving break. Yeah, so the idea there is to will be to use channels for synchronization. So the channels is the concept that used in the Go language, but we will implement channels in C. So effectively, channels provides some way to kind of combine both synchronization and parallel execution. That's how I would define that. So you would have an ability to send and receive messages. You have to implement the capability of sending and receiving messages between threads. So it can be used for synchronization, but it's also kind of to do some work, right? So it's kind of both tasks at the same time. So the idea of the interface will be like send, add message to the buffer. If buffer is full, block and wait. Then receive, that will remove the message from the buffer. If buffer is empty, it will block and wait. So that's already something that we have seen for the RIN buffer. But let me explain how we can actually use it. So it's not just a regular queue. You can actually do some operations with it. So let's say we can use channels to track resources, right? So we will, again, going back to the example that we have just now with semaphores, we can have like initialize number of channels to the number of CPU cores, and then we can do channel send and channel receive, right? So instead of sem wait and sem post. Also, you can use it you can also send data across using channels, right? So let's say, so the whole thing here is that the whole idea here is not just synchronization, but you can carry some data with this, right? So it's not just you're going to be blocking, but you also have a capability to send some data or receive some data. So let's say maybe we will have one thread will do channel send result, whatever, we'll do some computation, and then maybe we'll find the sum of sum of certain elements or whatever, right? So we split it in parallel threads. Each thread is executing some subtask, and then we calculate sum by having channel receive. So channel receive will effectively transfer the result from channel send. So the channel interface is that we have channel create, channel send, channels receive, channel close, channel destroy, and channel select. So those are the operations that we will have. So send and receive will be of two versions. So one version is blocking. That means if there is nothing to be consumed right now in channel received, that means it will block. In non-blocking version means if there is nothing to be consumed right now, it will return an error status. So it will say, I cannot get it, return false or something like that, right? And then channel send, the opposite. If the buffer is full, it will block. If you're using the blocking version, if you use non-blocking version, if the buffer is full, it will return an error status. So there's just some things to mention here. So basics for send and receive should be straightforward because that's pretty much producer consumer problem that we have looked at already, right? So in fact, today we looked at how we can use that, how we can solve this with condition variables, how we can solve it with semaphores. So pretty much, I guess 80% of the answer is already there, right? The only, I guess, difference here is that you will have to synchronize both sides. So here we have, here we assume that we have an unbounded queue in the slides. But you will have to make sure that you have, because you have a bounded queue here, you will also have to block when the buffer is full. So that's the opposite side also should be able to block.
Can you only hold one thing in the buffer?
One thing in the buffer, one element.
Like, yeah, like how many items does the buffer have?
Yeah, that's up to you. When you initialize the channel, you will decide how many elements you will hold in the buffer. So if you say I want to hold 10 elements, that's going to be when you'll specify when you create the channel. So the same thing, like 20 elements, maybe one element. You want to hold it one element, okay, you can initialize to one. Okay.
Is that a decision we make, or is that something the user would like it?
Well, so the way that it will work, you will implement channels, and then there is some tests. The benchmark will try to create, and with different parameters, and maybe it will try 1, maybe it will try 10, and so on. Maybe it will try 0, maybe it will try some invalid parameters, and make sure that you return error status correctly. So there is there is some tricky part with close. So when you call close, you need to make sure that threads that are already in progress, they are not stuck. So that's something that will require some, it's not a big deal actually, but still just have to be careful when you implement close. You cannot just close the channel and you have to unblock, potentially block the threads at that point. So also, I guess the most tricky part in the project will be select. So again, the basic send and receive should be straightforward. In fact, even if it's non-block conversion, it's straightforward. So for example, instead of some wait, you can do some try wait and something like this, right? So for non-block conversion, so POSIX threads allows you to use the non-block conversions of the semaphores. And the same deal if you use condition variables. There's there is a try version that means non-block conversion for condition variables. So I think I briefly mentioned it in our last lecture. So you can use those in the project description. It will actually refer to the manual and will say what you have to look at. But close just a little bit tricky, but not a big deal. But then the select is, I guess, the trickiest part. So that is to get the maximum number of points. So you need to figure out some way to properly block. So select basically allows you to make to specify multiple channels and do the operation on that, right? So and that may be a little bit trickier how you will do the synchronization at that point, right? So we'll get to this. I hope if time will, well, I guess we'll look at the basic today, and now next lecture we will look at the select. So what you can do there, just to give you some hint, when you read the project description, you can use extra structure to store some relevant data. Also, so there is also an extra credit part, so that may be also a little bit trickier, right? So we'll also have extra credit part for project free, but please do that only after you're done with everything, right? So make sure you implement the basic version first. So that's called unbuffered version. So there's buffered version when there is an associated buffer with the channel, and sometimes there's also a version where you can have unbuffered channel, and for that one, select becomes really tricky. So do that only if your time allows, right? It's much more complicated than extra credit that we had in project 2. So in fact, the amount of points is really small, right? So that not probably worth effort unless you really want to do something extra. So tests are not necessarily exhaustive, but we tried to include all this kind of tests to catch most errors. So potentially, if your stuff is buggy, we may add something extra. So and more specifically, like if you try to trick the benchmark to introduce some small delays, to avoid race conditions or data races, that is bad, right? So we can potentially catch those, right? And make sure you solve the concurrency problem correctly without any hacks. So you use semaphores. You can use semaphores. You can use condition variables. I personally prefer semaphores for this project because I think it's easier to implement with semaphores. But you know, some other people prefer conditional variables. That's fine. Yeah, so that's up to you. So we still have just a little bit of time. Let's look at some basic stuff so that you can get started with the project. So the channel create, you will specify the number of messages. So don't confuse, it's not number of bytes when you call channel send, channel create. So it's basically specifying how large your buffer is, how many messages you can hold. So one send means one message. Doesn't matter whether the send was like 10 bytes, 20 bytes, or whatever. So make sure you understand that. So it's not a size in terms of bytes, it's size in terms of like messages. So it will create the channel. So there is a special chan underscore T struct. You can look at this in the header file, and that will initialize that structure. So you have to initialize it appropriately. So you know, so you already has a buffer here because it's a buffered implementation, unless you do the extra credit. You know, so you know you can well, you actually have unbuffered for send and receive also. You will see that that's also, you know, that's not extra credit, but unbuffered select is the extra credit. So if you have a buffered version, you will have an associated buffer here, and then you can add any struct entries that you need after this. So it's up to you what you want to add in. What you can add after that. So how do you create a channel? Well, you have to use malloc, right? So you just allocate channel and then you know, create allocate it on the heap. So there is buffer create function to initialize buffer. So please use that. So there is some helper functions. You don't need to implement buffer because there is already buffer create. You know, maybe you kind of put mutex here and other things, it's up to you again, right? So you maybe will have some semaphores. Yeah, so please, that depends on your implementation. So yeah, for mutex, you use pthread mutex init. You know, for semaphores, you know, semaphore init and, you know, conditional variables. So you make sure you initialize everything in channel create. So whatever needed to be initial for creating a channel, initializing channel underscore T structure, that has to be done in channel create. So now there is a channel sent. So the channel is already initialized. Have to pass, okay, we have a pointer to this channel and then data. So data is opaque. So we don't know what kind of data we pass. It's just a pointer. And we have to store that pointer in a queue. So by the way, null can be also a valid message. So if you specify null, that should also be supported correctly. So again, it's just a finite, so channel is effectively a finite buffer. We already saw that we have an associated buffer with each channel. So just allocate whatever number of elements you need when you do create channel, when you create channel. So if you have to be holding 5 elements, you have to create buffer for 5 elements. If it has to hold 10 elements, you create buffer for 10 elements. So this buffer create will accept how many elements you need in the channel. So now the concern here is that many threads can call channel send. Channel create is of course called by one thread during initialization, but channel send can be already called by multiple threads. So you need a mutex for that. So when you try to modify the buffer, make sure you log you get the mutex and then unlock, just like the way that we did it in the slides, right? When we had this producer and consumer problem. So now the condition when the buffer is full or buffer is empty, this is when you need to use a condition variable or semaphore. We looked at both implementation today. So the only difference with today's whatever we have seen in the slides, today we assume that the buffer is unbounded. That means the producer can insert as many elements as it wants, but now the buffer is actually bounded. So if you have 10 elements, we cannot push more than 10 elements. So you have to also do synchronization on the producer side, not just on the consumer. It's pretty trivial. It's kind of like also you have to add another semaphore, another like you have another sem wait on the other side and sem post. So it's kind of like kind of similar idea, just implemented on the other side. But obviously the starting value of the semaphore will be different. So just think what the starting value will be for consumer and starting value for the producer. So now the channel receive, that again has the channel pointer, and the data, that's going to be a pointer for the data that you want to retrieve. So that's going to return the value, not in the previous case, we had the input value. Now it's void double star because it's an output, not input. So it removes one message from the buffer. Just use buffer remove for that purpose. Again, you have to call the mutex when you call buffer remove. And again, multiple threads can call channel receive. You need to use the same mutex. By the way, make sure you use the same mutex for both buffer and the buffer remove, because the same buffer has to be, whether you add or remove any messages, it has to be synchronized appropriately, right? So there is the same mutex. So now buffer is empty, or you need to wait. So that's different semaphore, as I mentioned, or different condition variable. So make sure you understand that. So on slide today, we just have seen one condition variable and one semaphore. So now you have to do that the same thing on the opposite side. So you have to have the second semaphore, the second condition variable. So just a quick question. Suppose you have a variable void result and you want to return parameter void double star. What are you going to do? So which answer is correct? So result contains the pointer void star. Okay, go ahead. It would be B, right? Yes, that's correct. So you dereference data because it's like a double pointer, right? And this is where you put the result. So actually, seeing some mistakes like this, make sure you do it correctly in channel receive. Make sure you understand what you're doing with the pointers. So just before we wrap up, one last thing I wanted to mention: blocking versus non-blocking. So blocking, waiting, like you use a regular semaphore wait, semaphore, condition variable wait, and so on. Non-blocking, the return would block status. So you can see the definition. There is already some error statuses would block. So there is no waiting. So the moment you discover that you cannot proceed, you immediately return. Yeah, so let's stop here, and that hopefully can already help you to get started with the project. And now next lecture, we'll look in more details at channel select and so on.